Good afternoon, everyone. My name is Lu Yixin. I'm from Indiana University. Today, I will present our paper together with my collaborator Xiaolong Bai from Tsinghua University. This is also joint work with Nan Zhang, my advisor Xiaofeng Wang, Xiaojin Tongxin, and Professor Shi Ming. So look at our title, Understanding and Mitigating the Security Risks of Apple Zero Configuration. So we are talking about Apple Zero Configuration today. So in terms of zero configuration, the first concept I would like to introduce to you is called Bonjour. Bonjour is a protocol. It's a protocol of zero configuration networking that's designed, proposed by Apple. So with Bonjour, Apple wants to provide the capability that with little or no configuration, you can easily add a new service to a network. The existing devices in this network can automatically find this new service and connect to it. So your network administrators, they no longer need to assign IP, hostname, service name to your services. As a user, you simply ask to see what network services are automatically available for you. And the only simple thing you need to do is to choose a service from a list. So let's take a quick comparison with the traditional network that required configuration. So in the network, even if you have a printer without configuration, you cannot connect to it. You have to configure the IP, the hostname, the DNS in order to connect. But in terms of usability, we don't like configuration. We want everything to be automatic. So we have Bonjour. So we want a service to configure itself automatically. We want your printer to configure its own IP hostname. We want the client to be able to automatically discover the services that are available without any pre-knowledge. So you want to know how. Take an example. So you want to add a printer to a network. Following Bonjour protocol, the printer configured itself through asking a couple of questions to the network. So the first one, is anybody using this IP? If no, the printer will take this IP. Second, is anybody using this host name? If no, the printer will take this host name. Also, the printer configured its service instance name if that's unique in the network. So the printer finished configuring itself. Next, let's see how a client is able to automatically discover this new printer. Oh, sorry. The client, the MacBook, asks a couple of questions to the network. Anyone has a printer service? The printer will say, I have one. Next, so on which host is this service? The printer will say, it's on host, blah, blah. So the client is able to find this new printer and add this printer to your printer list. So I have a question here for you. The printer has three attributes, the IP, the host name, the service name. So which of the three attributes do you think are saved in the list? Apple gives us the answer. Application store service instance name. So if the IP port or host name changed, the application can still connect. So according to Apple, it is the service instance name that is saved. So in the future, whenever you print to your saved printer, you print to a printer who owns this service name. So remember this equation. I will show you what this means to an attacker later. So our adversary. In the network, you always have uninfected devices. The attacker, we assume the attacker had control on one device in this network. The attacker aimed to intercept secret files transferred between those uninfected devices So in our previous example, the Mac and printer are uninfected, and the adversary wants to intercept the printing documents. So let's break zero configuration. And the first case is the printer. So in the network, the attacker has control on one device. The adversary claims that I have a printing service named blah blah, which is exactly the same name with the victim printer. So the printer, following Bonjour protocol, it will configure itself again and change it to a new service name. Recall our previous equation there. Your saved printer means a printer who owned this service name. So when you print to your saved printer, you actually print to the adversary's device, and the malicious device becomes the man in the middle. So why this happens? We know that there are 3 changing attributes that are self-configured. And Apple says you treat one of them as constant, and even if the other 2 changed, you can still connect, which just doesn't make sense. Also, a more fundamental problem is the lack of authentication in the protocol. The protocol anyone can claim any value of the 3 attributes, but the protocol only guarantees no duplicates, but not security. Let's take a look at our second attack case, attacking Apple AirDrop. AirDrop is used to transfer files, photos between Apple devices nearby. Let's take a look at a video demo to understand the normal AirDrop process. So the client finds all available devices nearby and just send a photo to the recipient from the list. Okay. This is the normal AirDrop process. So the AirDrop process also follows the Bonjour protocol. Let's take a quick example. The MacBook wants to drop a file to the iPhone, to Alice the iPhone. The MacBook will ask, anyone has an AirDrop service? The iPhone will answer, I have one, it's named blah blah. Next, so on which host is Alice's service? At this moment, if the adversary gives the answer that it's on host bobs.imac.local, if this answer comes first and the victim's reply comes second, then the MacBook will take it as Alice the iPhone had a service named blah blah, which is on host bobs.imac, which is totally wrong. So what happens next is, when the MacBook wants to drop a file to Alice, he will drop the file to the wrong host, bobs.imac, and the wrong host, the adversary, becomes a man in the middle. So you may have a question here. The AirDrop process uses HTTPS, and that the TLS help us. Does the TLS help us prevent this attack? The answer is no. So let's say if you connect to the wrong device using HTTPS, using the host name, you will find that that host is using a certificate issued to Apple ID.cdf blah blah. This is a valid certificate issued by Apple. The only problem is you have no idea who is the legitimate user behind this Apple ID. You will, actually, even if you connect to the right device, you will face exactly the same problem. Even if you connect to Alice the iPhone, you will find that Alice is using a certificate issued to Apple ID.abcd. You just have no idea who is the user behind this Apple ID. So basically, the certificate in AirDrop can hardly be used for authentication. So to better understand what's happening here, let's take a quick look at traditionally how a certificate can be used for authentication. When you connect to google.com, your browser will make sure that the domain you are connecting to matches the certificate. However, in AirDrop, the domain you are connecting to will never match the certificate. So this is the problem. So let's take a quick recap. The certificate in AirDrop cannot be used for authentication. Actually, as discovered in our research, we find that this is a fundamental problem, that linking a human to her certificate is complicated. There's a challenge in finding any identifiable information that are well-known, no privacy concern, and unique. That's the name can be duplicated. Date of birth, social security, email, all have privacy concern. And Apple still didn't find a good solution. This is what they did. And we believe this is still an open question, and we made our attempt in our paper to address it. So let's take a video demo to see the AirDrop attack. The sender is on the left. The receiver is on the right, both iPhones. The MacBook, the background MacBook is the attacker. So the attacker launched the malicious app from the desktop. The sender sent a photo. So the photo appeared on the attacker's desktop. The receiver also gets the photo. Yeah, this is the photo. So any file URL transferred through AirDrop between any Apple devices are subject to our man-in-the-middle attack. Besides Bonjour, we also studied some customized zero configuration protocols. For example, we find that one of them relies on customized TCP packets for service discovery and elliptical curved cryptography for authentication, but also failed the authentication due to the challenge in linking a human to her public key. For more details, please refer to our paper. Next, I would like to invite my collaborator, Xiaolong Bai, from Tsinghua University to continue this talk.
Okay, everyone, let's keep on attacking. And another vulnerability in Apple's zero configuration is multi-peer connectivity. Multi-peer connectivity is a framework for service discovery between nearby devices. With the help of MC, nearby devices can discover each other without user involvement. And it works both on Wi-Fi and Bluetooth. Here, MC uses an object called peer ID to identify each app using this framework. Peer ID has a few properties. For example, a public property called display name, which is customized by users, and a private property called unique ID, which is generated by MC and transparent to developers. During normal service discovery, the servers will test their peer ID objects, and the client will browse these test the peer IDs and show the display name. Even if two servers are created with the same display name, their unique IDs generated by MC will always be different. As a result, the client can distinguish them by their unique IDs and show two pairs. However, when the attacker accesses both client and server, it can also browse and acquire the peer ID object from the victim server. And then it can advertise using exactly the same peer ID object. However, the client cannot distinguish these two peer IDs because they have the same unique ID. And it will consider this attacker's peer ID as an update to the existing one. As a result, it will map the only peer ID to the attacker's address, which enables a successful man-in-the-middle attack. Besides these channels, we also look into zero configuration on Bluetooth, like handoff. Handoff is a service that lets iOS and OS X synchronize data through Bluetooth without user's configuration. When one handoff starts, it will create a Bluetooth channel between the iPhone and the Mac without user's involvement. And however, by exploiting this Bluetooth channel, a malicious app, even if the iPhone is not affected by any malicious app, a malicious app on the Mac can still steal the notification on iPhones. For more details about this attack, please refer to our paper. In summary, we have presented several attacks on Apple zero configuration channels, including Bonjour, AirDrop, MC, and handoff. However, there are more attacks beyond these. For attacks on other channels like BRE and customized zero configuration protocols, please refer to our paper. Please note that all these vulnerabilities we have reported to the vendors, and most of them have been acknowledged by the vendors. To understand the impact of the security risks in zero configuration techniques, we performed a measurement study. We analyzed the 61 popular Mac and iOS apps working with zero configuration. Among them, nearly 90% are vulnerable to man-in-the-middle or impersonation attacks. Here is a table of our measurement result. For example, in the Bonjour channel, we have sampled 22 applications, and among them, 18 are vulnerable. With these vulnerabilities, attackers can steal sensitive information like documents printed or instant message. So we need to think about how to protect these zero configuration techniques. Here, our defense mainly focuses on the fundamental problem, that is, linking a human to her certificate is complicated. Our solution is to let users speak out her certificate, which uses her voice biometrics to tie her certificate to her identity. We conducted a human subject study, which shows that our solution is well received by the users. For more details about this defense, please refer to our paper. In conclusion, our research shows that Apple's zero configuration techniques are not secure at all. The usability-oriented design of zero configuration totally affects its security. However, addressing such security risks is non-trivial due to the challenge in binding a human to her certificate. We have proposed our defense. It's called SPEC, and it uses the human's the voice biometrics to tie her certificate to her identity. Okay, that's all. Thank you. We now take questions.
Jaehyun Jung, Microsoft Research. So I've used AirDrop a lot with my husband, and then my experience was that when he sends something, I have to click that I'm receiving this data from Stuart's iPhone. Only then it sort of started transmitting. So I was wondering whether, but that's not what you showed in the video. So I was wondering whether that could be a fix for the problem that you indicated. So that's the question number one. And then number two is, so we looked at some HomeKit devices. So Apple has a HomeKit for these smart things, smart home devices protocols. And then we also found out that the HomeKit automatically discovers those HomeKit devices in the same networks for iOS HomeKit app. So have you looked at whether this could be also vulnerable for those zero configuration attacks?
Okay, for the first question, even if the user needs to click on the button, for example, accept, it also is affected by our attack. Because the attacker, the man-in-the-middle attacker, can just accept the photo and then transfer the photo to the victim receiver. And then the victim receiver will still have this accept button. I think it's still vulnerable.
Yeah, the attack is totally transparent to the recipient. It's totally same. So
Yeah.
that the attack is still C. The accept button, in our attack, the recipient also need to click the accept button to get the.
But I guess I'm surprised that this confirmation button doesn't take any part
No,
in the
it doesn't.
No, doesn't.
Also, regarding your second question, we didn't look into the HomeKit thing a lot, but in our research, we also look at the Apple TV. The Apple TV also use the boundary protocol. It's also vulnerable to our amendment attack. So you input something, you use your remote control to give some input to the Apple TV. We can also intercept that message. I think, yeah.